Parallel feeders have specific requirements according to the National Electrical Code, or NEC. Let's explore some common code violations related to parallel feeder installations and discuss corrective actions. Firstly, a critical requirement is the presence of an equipment grounding conductor, or EG, in all parallel feeder conduits. The code mandates that an EGC must be installed in each conduit containing parallel feeders. Secondly, parallel feeders must use the same insulation type throughout their entire run. Mixing insulation types like THHN and TW is not permitted because they possess different dielectric properties. This difference can lead to uneven current distribution and potential safety hazards. Addressing the violation of a missing EGC in rigid galvanized steel, or RGS, conduit involves installing one. This requires pulling an EGC wire through the RGS conduit and connecting it to the main equipment ground bus. To correct the issue of dissimilar insulation types, you'll need to replace the existing insulation in the RGS conduit with THHN insulation. This involves removing the TW insulation from the conductors and installing THHN insulation in its place. Ensuring the EGC is properly connected to all panels is crucial. Verify that the EGC is connected to the ground bus in each of the 3 panels being fed. Beyond these primary violations, several other factors warrant consideration. Conduit size is a key concern. A 4-inch RGS conduit might not be sufficient to accommodate the 600 Nm parallel feeders, the required EGC, and any additional conductors. Evaluating the conduit fill is necessary to determine if a larger conduit size is needed. The distance from the paralleled 600 Nm conductors to the tapped 500 Nm conductors is limited. The NEC specifies a maximum distance of 10 feet for these taps. Exceeding this distance can affect the overcurrent protection and conductor ampacity. The 400 amp breaker size is appropriate for the size of the 600 Nm conductors, but it's important to verify this based on the specific installation conditions and conductor ampacity ratings. The combination of the 600 Nm parallel feeders and the 500 Nm tapped conductors can potentially result in high ground fault current levels. In such cases, consider installing a ground fault circuit interrupter, or GFCI, or ground fault protection, or GFP, device to enhance safety and protect against electrical faults. Now let's delve into the technical aspects of each of these points. Equipment grounding conductors are vital for providing a low impedance path for fault current to return to the source. This low impedance path facilitates the rapid operation of overcurrent protective devices like circuit breakers or fuses, effectively clearing the fault and minimizing the risk of electrical shock or fire. When an equipment grounding conductor is absent, as in the case of the RGS conduit without an EGC, the fault current path becomes less defined and potentially higher in impedance. This can delay the operation of overcurrent devices, increasing the duration of the fault and raising the risk of damage or injury. According to NEC 250.4 A5, non-current carrying metal parts of equipment must be grounded. This includes metal conduits, enclosures, and other conductive components. The purpose of this grounding is to minimize the voltage potential between these metal parts and ground, thereby reducing the risk of electric shock. The equipment grounding conductor provides the necessary connection to ground, ensuring that any fault current can safely flow back to the source. The NEC also addresses the sizing and installation requirements for equipment grounding conductors in Article 250. The size of the EGC is typically based on the size of the ungrounded conductors in the circuit, as specified in NEC Table 250.122. The EGC must be installed in the same raceway or cable as the circuit conductors to ensure a low impedance path for fault current. Regarding insulation types, THHN and TW insulations have distinct characteristics that make them unsuitable for use together in parallel feeders. THHN insulation is a thermoplastic high-heat resistant nylon-coated insulation, while TW insulation is a thermoplastic water-resistant insulation. THHN insulation typically has a higher temperature rating, such as 90 degrees Celsius in dry locations, compared to TW insulation, which may be rated at 60 degrees Celsius or 75 degrees Celsius. This difference in temperature ratings can affect the ampacity of the conductors and the overall performance of the parallel feeder system. Moreover, the dielectric properties of THHN and TW insulation differ. The dielectric constant, which measures a material's ability to store electrical energy in an electric field, varies between these insulation types. When conductors with different dielectric constants are used in parallel, it can lead to uneven current distribution among the conductors. This uneven current distribution can overload some conductors while underutilizing others, potentially causing overheating and insulation failure. The NEC requires that all conductors in a parallel set be of the same insulation type and have the same electrical characteristics, as stated in NEC 310.10 H. This ensures that the current is evenly distributed among the conductors and that the system operates safely and reliably. Corrective actions such as installing an EGC in the RGS conduit and replacing the TW insulation with THHN insulation are essential to comply with the NEC and ensure the safety of the electrical installation. When installing an EGC in the RGS conduit, it's important to select the appropriate size EGC based on the size of the ungrounded conductors, referring to NEC Table 250.122. The EGC should be securely connected to the main equipment ground bus and to the metal enclosure of the RGS conduit. When replacing the TW insulation with THHN insulation, ensure that the new conductors are properly sized for the load and that they are installed in accordance with NEC requirements. The NEC provides guidelines for conductor ampacity in Article 310, and it's crucial to follow these guidelines to prevent overheating and insulation damage. Now, let's consider the other factors that warrant attention, such as conduit size. The 4-inch RGS conduit may not provide sufficient space for the 600 Nm parallel feeders, the egg, and any additional conductors required by the NEC. The NEC specifies the maximum allowable fill for conduits in Chapter 9, Table 1. The conduit fill is the percentage of the conduit's cross-sectional area that is occupied by the conductors. Exceeding the maximum allowable fill can make it difficult to pull the conductors through the conduit, damage the insulation, and reduce the conduit's ability to dissipate heat. To determine if the 4-inch RGS conduit is adequately sized, calculate the total cross-sectional area of all the conductors, including the 600 Nm conductors, the egg, and any other conductors, such as control wires or communication cables. Then compare this total area to the allowable fill area for a 4-inch RGS conduit, as specified in NEC Chapter 9, Table 4. If the total conductor area exceeds the allowable fill area, a larger conduit size is necessary. The distance from the parallel 600 Nm conductors to the tap 500 Nm conductors is another important consideration. The NEC limits the length of taps from parallel conductors to ensure proper overcurrent protection. According to NEC 240.21 B, tap conductors must not exceed 10 feet in length when tapped from conductors protected at their ampacity. This 10-foot tap rule is intended to prevent the tap conductors from being overloaded in the event of a fault on the load side of the tap. If the distance from the parallel 600 Nm conductors to the tap 500 Nm conductors exceeds 10 feet, the tap conductors must be protected by an overcurrent device at their ampacity. This overcurrent device must be located at the point where the tap conductors connect to the parallel conductors. The 400 amp breaker size is appropriate for the size of the 600 Nm conductors, assuming that the conductors are rated for at least 400 amps. The NEC provides ampacity tables for conductors in Article 310, and it's crucial to select conductors with an ampacity that is equal to or greater than the rating of the overcurrent device protecting them. However, it's important to verify this based on the specific installation conditions and conductor ampacity ratings. Factors such as the ambient temperature, the number of conductors in a raceway, and the type of insulation can affect the ampacity of the conductors. It's also important to ensure that the overcurrent device is properly coordinated with the conductor ampacity to prevent nuisance tripping and ensure adequate protection against overloads and short circuits. Ground fault protection is a critical safety measure, especially in large electrical systems with high fault current potential. Ground faults can occur when a phase conductor comes into contact with a grounded surface, such as a metal enclosure or a water pipe. The resulting fault current can be very high, potentially causing significant damage and posing a serious risk of electric shock or fire. Ground fault circuit interrupters, or GFCIs, are designed to detect ground faults and quickly interrupt the circuit, typically within milliseconds. GFCIs are commonly used in residential and commercial applications to protect people from electric shock. Ground fault protection, or GFP, devices are similar to GFCIs but are typically used in larger electrical systems to protect equipment from damage. GFP devices can be set to trip at higher current levels than GFCIs, allowing them to protect against ground faults without causing nuisance tripping. The NEC requires ground fault protection for certain types of equipment, such as service equipment and feeders that supply sensitive electronic equipment. The specific requirements for ground fault protection are outlined in NEC 230.95 and 215.10. In summary, parallel feeders are subject to specific code requirements to ensure safety and reliability. Addressing violations such as missing equipment, grounding conductors, similar insulation types, and improper conduit sizing is essential for compliance with the NEC. Additionally, considering factors such as tap conductor length, of current protection, and ground fault protection can enhance the overall safety and performance of the electrical system. By adhering to these guidelines and best practices, electrical professionals can ensure that parallel feeder installations are safe, efficient, and compliant with the NEC. The NEC is updated regularly, so it is important to consult the latest edition for the most current requirements. Remember that electrical work should only be performed by qualified individuals who are familiar with the NEC and local codes. Always prioritize safety when working with electricity and follow all applicable safety procedures.